Hello, y'all. This is Darrell Lee Berry Jr. back doing some reading of linear algebra. Uh, I have class later today. Adjust my camera a little bit. I have class later today, and I figure we'll be going through 1.5 in the book. We have homework on that coming up, even though it's not scheduled yet. So I'll start going through this section. Ironically, there's a section that has to do with the project that we're on. Some of you who saw the video earlier know that I was looking at how to go from a parametric to a Cartesian uh, uh, form of a system. The process of doing it for a R2 system, like a line, is different from an R3 system, like a plane. So, but I got that from chapter 1.5, so I'm sure we'll get to it. So here are my links. Make sure you join my Discord. We can talk about science and math and all that good stuff. Sign up for Patreon. There's my X. You could join there. This is my YouTube channel. Make sure again you like and subscribe. And what we'll do is go ahead and get started with the chapter. I do offer tutoring. I've tutored math before. I've tutored and been a learning assistant for science before. EM exactly, electromagnetism, is a undergraduate physics class. I'll be doing that again in the summer and the fall. So let me know if you like some tutoring. You can sign up either through PayPal or through uh, Patreon, and we can get that going. So why don't we, to be 1.5, I may do a full screen this time. Right? So we'll see how this works. So that'll be the screen for the book. And when I do a writing, something that's necessary to write, I'll just open that up. So the theory of linear systems. We developed Gaussian elimination as a technique for finding a parametric description of the solutions of a system of linear Cartesian equations. Now, I actually don't like Gaussian elimination. If I'm understanding that correctly, that's basically going through the equations like this, but I actually prefer to put it into a matrix. So but I actually skip 1.4 because I was familiar with matrices, at least matrix row reduction. Now we shall see the same technique allows us to proceed in the opposite direction. That is, given in vectors, we would like to find a set of Cartesian equations whose solution is precisely span V1 through Vk. In addition, we will rephrase in somewhat more general terms the observations we have already made about solutions of systems of linear equations. So that would explain why I found the answer in this section. So So, theory of linear systems, that's going from uh, parametric to Cartesian. Interesting case, by the way. Let me hop in Discord in case anybody were to join, so you can see me there if you would like. And the Discord link is scrolling at the top of the screen. Discord .gg slash 9JCPX2P9, and that should get you into the main discussion room. So back to the book. right? So existence, constraint equations, and rank. So we have talked about rank. So technically we have started this section, just didn't realize it was this section. So let's go to the split view. Suppose A is an n by n matrix. There are two equally important ways to interpret a system of equations. AX equals B. In the preceding section, we concentrated on the row vectors of A. Okay, so apparently, if you have A, that's the same thing as row vectors. Row vectors. A, let's see, A1, A2, AM, because the first symbol is the first component is a row, and then should all be the same as A11, A12, A13, A1N, A21, A22, A23, A2N, AM1, AM2, AM3, AMN. So basically, these are the row vectors. And just like you could also make them a column vector. Then the vector C is a solution of AX equals B if and only if. So for the solution, right? So let's look at this. So we have AX plus AX equals B. That means that some matrix A times some vector, which will necessarily be N times something, equals, I guess I should say N times P is going to equal MP. So for in order for this to work, X is the solution. So X equals C is what I'm thinking you mean. And that's what we're solving for. So whatever this vector is, it works with all of them. So basically you'll end up with, so if you have so many rows, you have, why don't I color code this a little bit better? We have each of these dot products with the same thing. It's going to equal that part. So this equals B1, this is B2, and 3, and so forth. So that seems reasonable. Geometrically, C is a solution precisely when it lies in the intersection of all the hyperplanes defined by the system of equations. So C is a solution if and only if It lies in the intersection of all the hyperplanes defined by the system of equations. On the other hand, we can define the column vectors of the MN matrix as follows. So now we're doing the column vectors. The row was A1, A2, all the way to AM, and column is AJ. That's just the matrix. Column AJ equals A1J, A2J, ANJ, and it's in RM, which means the rows can't be more rows than the number of rows in the matrix overall, and J equals, we can say, to make this more succinct, J goes from 1 to N, all right? Which is what we have here. We saw that when we broke this matrix up. So we see 1, 2, 1, 2, all the way up to M for that column. And then I is the number, at least J for this problem is the number on the right side. So we have that. We now make an observation that will be crucial in our future work. The matrix product AX can also be written as this. So we're going to write this out. You know, the book skips a lot of steps all the time. So AX equals, and we'll call this, as our example, let's do 2 by 3, and let's do 3 by 1 as an example. So this is A1, 1, A1, 2, A1, 2, A1, 3, A, mix these up, 2, 1, A2, 2, A2, 3. So that's a 2 by 3 matrix, 2 rows, 3 columns. And this will be x1, x2, x3, or x11, x21, x31. So that is going to equal x11, a11, a21, plus x21, a a12, a22, plus x31, a13, a23. All right. So I'm making sure I do all the different steps, and it looks like they put A first, so I'll do that. So that's A11, X11, A21, x11 plus a12 x21 a22 x21 plus a13 x31 a23 x31. So I see. So they actually skipped this step and came, so this is like an extra step from what they wanted, but that is accurate. But they said that x1 and the column vector of the first column plus x21 times the column vector of the second column plus x31 plus the column vector of the third column. So this is the column, this is the row by column, which is 1, 1, 2, 1, 3, 1 because there's only one column. Thus, a solution C of the linear system AX equals B provides scalars C1 through Cn so that, and this is going to equal B. So this equals C1 A1 plus C2 A2 plus C3 A3, which is for the particular rows B. So that means that this is a row, this is a column, and as we saw here, we take each row and multiply it by the related column. This is our second geometric interpretation of the system of linear equations. A solution C gives a representation of vector B as a linear combination C1A1 all the way through CNAN, in our case, C3A3. And it happens to be the same. So the number of columns has to equal the number of rows because each row has to match with each column. So we have that. So, yeah, that seems sufficient enough. Pretty self-explanatory, I guess. So let's look at this example here. Consider the four vectors. Suppose we want to express the vector B as a linear combination of vectors v1, v2, v3. Write out the expression x1, v1, x2, v2, x3, v3 equals x1 first column, x2 second column, x3 third column equals b. To obtain this system of equations, in the matrix notation, we must solve AX equals B where the columns of A are V1, V2, V3. So we take the augmented matrix. This tells us that the solution is negative 203 as a column. So B is that, which is as the reader can check works. So we get A from the vectors. We want that to be a linear combination of those three. So we need to find some X. So we have A is given. We have given as V1, V2, V3. And we have B given. In order for AX to equal B, we have to solve for B by solving the system of equations. Right? So we have that. So now, for example, 2, we would like to express the vector B prime as a linear combination of the same vectors V1 through V3. This then leads analogously to the system of equations. So just basically did the same thing, equating them, resolving the augmented matrix. Same left side, different right side, and then solve. So this means whenever you have a bunch of zeros equal to 1, the matrix has no solution. So B, that B, cannot be a solution of that system, or at least there's no way to solve that system of equations so it equals that B. So definition, if the system of equations AX equals B has no solutions, so the system is inconsistent. At least one solution is consistent. So I remember us talking about consistent and inconsistent in class on Thursday of last week. We had a test Tuesday. Those of you who watched the previous videos this week know. And I think I did well on it, by the way. So also I remember it being said that, well, I guess we'll get to that. Let me check what that note said, actually, before we move on. I was thinking about something else. I was thinking about rank. I was thinking about singular and non-singular. So I was thinking about something different. All right. A system of equations is consistent precisely when a solution exists. We see that the system of equations in example 2 is inconsistent, and the system of equations in example 1 is consistent. It is easy to recognize an inconsistent system of equations from the echelon form of its augmented matrix. The system is consistent precisely when there's an equation that reads all bunch of zeros equals some number that is non-zero. When there's a row in echelon form of an augmented matrix, all of whose entries are zero except for the rightmost. Turning this around a bit, let U C denote an echelon form of the augmented matrix AB. The system AX equals B is consistent if and only if any zero row in U corresponds to a zero entry in the vector C, which makes sense because if C equals zero, then it's inconsistent if the left if Z equals non-zero, if C equals non-zero is inconsistent if anything on the left is everything on the left is zero. There are two geometric interpretations of consistency. From the standpoint of row vectors, the system AX equals B is consistent precisely when the intersection of the hyperplanes is non-empty. Okay, so there is an intersection of hyperplanes, and I'm forgetting the definition of hyperplanes as in that form. So it seems like it's saying A dot X equals B is a hyperplane, but I do remember as a throwback from an earlier class, an earlier section of the book that is, we did find that A dot X equals A dot XO equals some number when the plane is shifted from zero. So this is the origin. A dot X equals A dot X sub O equals C is shifted, and if the plane is at the origin, then A dot X equals zero. So basically every dot product is a plane, at least if it's in R3, definitely. And of course, we would end up with A1 X1 plus A2 X2 plus A3 X3 equals zero. And A would then be the normal vector to the plane. And those 3 points would be the point. So yes, it's a good refresher. From the point of view of column vectors, the system AX equals B is consistent precisely when the vector B can be written as a linear combination of the column vectors A1 through AN of A. In other words, it is consistent when B spans A1 through AN. Makes sense. In the next example, we characterize those vectors B and R4 that can be expressed as a linear combination of the three vectors V1 through V3 from examples 1 and 2. So let's actually do this example here. So you want example 3 for what vectors B equals B1, B2, B3, B4. Will the system x1 plus x2 plus 2x3 equals B1, x2 plus x3 equals B2, x1 plus x2 plus x3 equals b3. 2x1 plus x2 plus 2x3 equals b4. Have a solution. Okay, so we form the augmented matrix. So we know this is the symbol of an augmented matrix now. So we have 1, 1, 2, b1, 1, 1, b2, 1, 1, 1, b3, and 2, 1, 2, b4. So now let's go ahead and do this ourselves. See how this works. So we have, let's do row 1 minus row 3 minus row 1 to row 3, and row 4 minus 2 row 1 to row 4. So 1, 1, 2, b1, 0, 1, 1, b2. So minus row 1. That's 1 minus 1 is 0. 1 minus 1 is 0. 1 minus 2 is negative 1. And b3 minus b1. And then we have minus 2 row 1. So 2 minus 2 is 0. 1 minus 2 is negative 1. 2 minus 4 is negative 2. And b4 minus 2 b1. So what I'll do is add R4 plus R2 to R2, and R4 plus R1 to R1. So that's going to be R4 plus R1 is 1, 0, 0. B4 minus B1, and R4 plus R2, 0, 0, negative 1. B4 plus B2 minus 2B1. And then we'll also add, no, mind, let's just write this out first, 0, 0. Actually, let's go ahead and multiply this by negative 1. 0, 0, 1, B1 minus B3. The swapping the signs makes that negative. And then we have, I'll multiply this by negative 1 after that. So we have 0, 0, 1, 2, and 2b1 minus b4. So why don't we do row 2 plus row 3, and that's going to be row 3, and 2 row 2 plus row 4 to row 4. So I'll repeat the top line. I'll multiply that later. And what do we have? Row 2 plus row 3 is row 3. So that's 0, 0, 0. And now we have row 2 plus row 3. So that's B4 plus B2 minus B1 minus B3. And then 2 row 2 plus row 4. So that's going to be 0, 0, 0, 1. 2 times row 2 plus row 4 is minus 2. Then we have 2B4 plus B4. That gives me B4. We have 2B2. We have minus 4B1 plus 2B1. And then we have minus B4 again. So that'll get rid of this B4. Or did I do that already? Yeah, did that already. So we had 2B4 plus B4, 2B2 minus 4B1 and 2B1. All right, that seems to be okay. And I'll do one more thing and multiply this by -1. And I'll swap the rows around a bit. So we have 1, 0, 0, B4 minus B1. Now move this second, 0, 1, 0, B4 plus 2B2 minus 2B1. And I'll swap the signs of this one, 0, 0, 1. Now we have 2B1 minus B2 minus B4. Then we have 0, 0, 0, B4 plus B2 minus B1 minus B3. So let's see how I did. Notice they have a lot more ones. The bottom row seems to be the same. Minus B1 minus B3 plus B4 plus B2. So that is the same. It looks like they can easily add some rows around between the first and second row and get rid of those zeros. And then they would also have the same thing I have. But I noticed that they put it in echelon form, not reduced row echelon form. So that's the difference. Okay, so if you put it in echelon form, not reduced row echelon form, it makes it simpler. So if I did, for instance, plus row 2 and plus 2 row 3, I would get it back to where it is, but I'll just leave it the way it is. So we have to remember that it's echelon form, not reduced. So just get a bunch of zeros at the bottom. These are the only zeros we need. But still, this is the constraint equation, so it still gets us the constraint equation. So it's not that it's wrong, it's just more work than what's needed. We reduce that the original system of equations will have a solution if and only if. Ah, so that's why this is the constraint equation. If and only if negative b1 plus b2 minus b3 plus b4 equals 0. That is, the vector b belongs to span. So b is in span v1, v2, v3 when b satisfies the constraint equation, right? Easy enough. So they give another example. It's pretty much the same thing. Let's do it though. Example 4. So we have a equals 1, negative 1, 1, 3, 2, negative 1, 1, 4, negative 3, 3, negative 3, 3. And we look for a constraint equation that describes the vectors b. Remember, the constraint equation is the plane describing that system. For b in R4 and ax equals b. All vectors b that can be expressed as a linear combination of the columns of A. Consistent means all vectors b that can be expressed as a linear combo of columns of A. And remember, that's because the rows of B are moved over and multiplied by A in such a way that each row is multiplied by an entire column of A, like we did with the derivation up here. So each row of B multiplies by a column of A. Therefore, that row is expressed, the linear combination of that row ends up equaling B. And actually, this is X. The linear combination of X times the column of A equals B. That's the best way to word it. I feel like I'm not wording this the best way, but hopefully the visual of it is clearer. When this column hits that, when this row hits that, the yellow row hits the yellow column, the green row hits the green column, the blue row hits the blue column, that first row, A11, A12, A13, is the linear combination representing B1, and A21, A22, A23, when dot product with that X, with all the X's. So now you have this basically. B1 is a linear combination of the first row, and B2 is a linear combination of the second. So even though I did too many steps, it is illustrative here. So that's probably the best way to explain it, show it like that. And you end up having this. So, and they each end up making a linear combination with either B1 or B2, right? So as before, we consider the augmented matrix. We go to echelon form, not reduced echelon form. So we can say, now we're going back to the example 4 with this matrix here. So we can say A, B equals augmented matrix equals 4 negative 1, 1, 3, 2, negative 1, 1, 4, negative 3, and 3, negative 3, 3. And we're going to, uh, yeah, that's correct. Now, right, we're solving, basically we're solving for x. So ironically, this is like saying x1 equals that, x2 equals that, and x3 equals that. And, but they all can work only if that is consistent. So I have to recall how to input the x's in there. But we'll see. We'll keep going. And let's go ahead and do the echelon form of this. Let me make sure my matrix is correct. All right. So we'll have, actually, let me move this down for room. So we'll say, row 2 minus 3, row 1, 2, row 2, row 3 minus row 1, row 3, row 4 minus 3, row 1, row 4, and let us see. So I go back and forth on the most um, organized way to do this. Sometimes I write what I'm subtracting here. Like for instance, since I'm subtracting row 1, I might write 1 minus 1 plus 1. But sometimes that gets too cumbersome. At the same time, sometimes when I don't make a note like that, I add or subtract incorrectly. So it's a, I guess, use a common phrase, a crapshoot. So I think I'll just try to just do it in my head instead of writing at all and see how that helps. So let me write the first line. So we have row 2 minus 3, row 1. So 3 minus 3, 0. Right, so minus 3 times that. So it's plus 3. That's 5 minus 3, negative 4 minus 3, B2 minus B1. And then it's just row 3 minus row 1. So 1 minus 1 is 0. 4 minus negative 1 is plus 1 is 5. Negative 3 minus 1 is negative 4. And B3 minus B1. Pretty sure I meant to write 3B1 here. Maybe I said it, but just didn't write it. And row 4 minus 3, row 1. So 3 minus 3, 0. Negative 3 minus 3, negative 1. So plus 3 times 1. That should be 0. And then 3 minus 3 is 0. So we already have our restraint equation. So that's B4 minus 3B1. Now all we need to do now is get a bunch of ones in the diagonal. And, no, actually, this. We can do row 3 minus row 2 to row 3. So that's going to be row 3 minus row 2, 0. 5 minus 5 is 0. Negative 4 minus negative 4 is 0. And this is going to be B3 minus B2. And negative B1 plus B3 is plus 3B1. Then we have 0, 0, 0 is B4 minus 3B1. So let's take a look at the book and see how far they took us. All right, so we got where the book got. They have 1, negative 1, 1, B1, 0, 5, negative 4, B2 minus 3B1. Bunch of zeros is B3 minus B2 plus 2B1. Oh, hold up, F3. So what did I do wrong with the B1s? Oh yeah. So I have minus 2B1. B3 minus B2, negative 1 plus, oh yeah. So it's negative 1 plus 3, so that's my negative 2. So that meant about sometimes I mess up the numbers. So we have 0, 0, 0, B3 minus B2 plus 2B1. We have a bunch of zeros, B4 minus 3B1. So let's see what they do with the fact that we have two different constraint equations, seemingly. So we have here, we have two rows of zeros in U. So this all equals U. And how did they term it? C. All right. So the original one, the augmented matrix, is AB. The reduced one is UC. So here you have two rows of zeros in U. So we conclude that AX equals B is consistent if and only if, B satisfies the two constraint equations. Okay. So we have two. I was thinking we was going to have to simplify them to combine them or solve for one of them, or like insert one into the other one. Like you could make 0 equals B4 minus 3B1. So B4 equals 3B1. So B1 equals B4 divided by 3, and just substitute that in there. But they would know. So we have 2b1 minus b2 plus b3 equals 0, and negative 3b1 plus b4 equals 0. These equations describe the intersection of two hyperplanes through the origin of R4 with respective normals. Interesting. So we have N1 equals 2, negative 1, 1, 0 of plane 1. And we have N2 equals negative 3, 0, 0, 1 of plane 2. So these equations describe the intersection of two hyperplanes through the origin in R4 with respective normal vectors. Two hyperplanes through the origin in R4 because it's equal 0. So that's how it's through the origin with normal vectors in 1 and 2. All right, we see right there how to get the plane through the origin. And I suppose even if the last one equals something, I mean, is each of these a plane? It's only the ones that equal 0 is a plane. So I guess if you have a plane, this is going to always reduce to 0, is what I'm assuming. At least one row will reduce to 0. Notice in the last two examples, we have reversed the process of section 3 and 4. There we express the general solution of a system of linear equations as a linear combination of certain vectors. Just as we described lines, planes, and hyperplanes parametrically earlier. Here, starting with the column vectors of matrix A, we have found the constraint equations that a vector B must satisfy in order to be a linear combination of them, that is, to be in their span. This is the process of determining Cartesian equations in a space that is defined parametrically. There we go. So to find a Cartesian equation from a system expressed parametrically, use row operations to the, it was only the echelon form, right? Echelon form to find one or more constraint equations. Awesome. Easy enough, right? And there's a brief remark here. It is worth noting that since A has different echelon forms, one can arrive at different constraint equations. We will investigate this more deeply in chapter 3. So remark, there can be different constraint equations. Just like multiple equations can describe the same thing. So it seems like a good place to stop. We're going to just about an hour. If you have any questions, any comments, please leave them in the comment section at the bottom of the video, or sometimes they're putting it to the side. Like, subscribe, share, join my Discord, and let me know if you're interested in any tutoring. Here are all of my links again, and I'll go ahead and put a pause on it for now, and I'll be back either later or later this week, and we'll go ahead and mechanics. We'll go ahead and do some quantum mechanics, definitely. Some more linear algebra, of course, and we'll see what else we can do. So, boom, all my links: STEM, YouTube, Patreon, X, and be sure to join my X. And here's my outro.